Yes, so let's continue. We saw before the break that we can set a threshold. We also saw that we get some false positives and negatives, and now this part will be about actually how we can measure it and quantify how well we are doing. So let's load this image. It's some microscope image of cells, and we can see the mitochondria. This is a quite messy image, and someone has been kind enough to label it for us. I think this is data from EPFL. They have an image data bank where you can download these images. And it's an easy one. We have black is the background, and the white is the mitochondria, the foreground. And now let's see what we can do. We can first of all classify, assign the images in different ways. Ideally, we have all as true positives, that is actually labeled as foreground and is also foreground. We can also have true negatives, which is the background, the correct background, labeled as background. Though, with noise and variations in material composition, we can also get some misclassifications. So we can have false positives, which is in principle a background, but it's labeled as a foreground. And then we can have false negative, which should be labeled as a foreground, but turned into a background. And to confirm this, we actually need to have a ground truth, because we can't say anything without knowing what the truth is. And then it's the question of how the quality of this ground truth, but that's another question. So let's try putting a threshold on it, same way as we did before. We just set the threshold, saying a cell image greater than the threshold is the mitochondria. Looking at the histogram, we see that we actually have two bumps. So there is some separation between background and some foreground. But when we put this threshold, you can see that there is a lot more than the mitochondria that was segmented. And in the mitochondria, there are also gaps. So it doesn't really look like what we would expect in this one. So how can we quantify this? One way is to compute or separate it into the four classes. We have the true negatives, we have the true positives, false negatives, and false positives. And that gives us an image of, or a picture of, in which direction we are doing right or wrong. Apparently, with this threshold, we don't do very many false negatives, but that's also due to the fact that we don't have so many mitochondria. So they are more rare. I don't know, it's maybe 10% of the image, so there is not so big chance to do a false negative. And then we have the true positives, look pretty okay, and the false positive looks like we have the whole network behind that is misclassified. This can be a bit formalized into something called a confusion matrix. We already had it in lecture 2, and now we're going to use it in more detail. So here we have, again, we can put some percentages for the different parts here. A different way to visualize it is to combine all the 4 images I had in the previous one into a single one and color code the values depending on what it is. Can also be, it gives you also an idea where these misclassifications actually are. So you can see that the false negatives, they are mainly within the mitochondria, whereas the false positives, they are all outside of them. So that gives us also an idea where we should put our effort and what kind of structures we should target to reduce. Some metrics that we can use to quantify this, that's recall and precision. And in principle, recall tells us how many we detected versus how many we expected. So that is the true positives over the true positives plus the false negatives. So that is what we expected to have. Precision is a bit different than is expected versus detected. And then we have, again, the true positives, but this time we have true positives plus false positives. And that gives us the other side of the story. And for our images, we had a recall of 82 and precision of 18. Ideally, we want to push these into ones. That would be the best case for both of them. So the recall is pretty good, but the precision is rather bad in this case. And that can also be, if we go back here, that can also be seen that we have a very large amount of false positives, and that brings down this value. There we have it. Another way to visualize it is using something called a receiver operating characteristics. That is a tool that was developed during World War II when they wanted to, when they started developing the detection theory, and in particular for radar applications. Did we detect an enemy plane or not? And on the radar. And right now we have only played with a single threshold, but what happens if we scan the thresholds and see how the system responds? And for that we need to compute a lot of hit and miss statistics for all the cases. So create a table, we have thresholds scanning from one value to another, and then we see what is our hit rate in different categories. If we just look at the single point that we did before, we had this, no, that's a different value actually. Anyway, doesn't matter. So let's say we had put the value 0.5 as a threshold. Then we get the true positive rate, so the recall was pretty strong, and the false positive rate was relatively low. Ideally, you want to be up in this corner, so you have no false positives and all true positives. But that's usually hard to achieve. In some cases, you can have pretty good stuff. Depends on the image composition and what the algorithm that you use for the segmentation. So let's try it for this mitochondria image. And we see that, first of all, the green line here tells us that you're better off, if you're below that, you're better off just tossing a coin. So that would be random guessing. And for our example, we get a curve like this. And at some point, it flattens out. That means if you start increasing the threshold, you only get more false positives, and you don't want those. So you probably should stop doing things around here. So you have to accept some degree of misclassifications on the positive side. To improve it, we have already seen that with filters we can improve the signal-to-noise ratio. So let's throw in a bunch of filters. In this test, I have set up, no filter is the same as we had before. We have a Gaussian filter, we have difference of Gaussian filter, and we have a median filter. And what we can see is that the no filter, well, that's what it is. And then we have the Gaussian filter. You can see the blurring. Important here is to see that you have less structures inside the mitochondria. And maybe that these structures here get a little bit lower, smeared out, lower intensity. Difference of Gaussian is actually a high-pass filter, so it enhances the edges. And well, let's see how it performs. In this case, I don't think it's very helpful. And the median filter also takes out some of these structures, but not as much blurring as the Gauss filter. So if we run the segmentation, all these images, we get the following RSE curves. And in principle, the Gaussian filter performed the best, and the reason is that it actually suppressed the thin structures a bit and smeared out within the mitochondria. The median filter, which is second best, did some smoothing, but it didn't manage to reduce all the tiny details within the mitochondria. So that's why it's not performing as good as the Gauss filter. Finally, we have the non-filtered is slightly worse than the median. And finally, we have the high-pass filter, which is partly like random guessing, or more or less like random guessing, because you don't have, in principle, the kind of information that you want to extract. So that was really the wrong kind of filter for this application. But these curves, they are curves, so they are not easy to just put in a table and see which one is performing the best. So what is often done and also used in machine learning algorithms is to compute the area under the ROC curve, and then we get a scalar instead, and that's much easier to compare the performance. Before I could say, yeah, that one is a little bit better because it goes farther out, but now we have the confirmation that the area under the curve is clearly best for the Gaussian. And when you do iterative segmentation algorithms, machine learning, etc., then this is a pretty good value to see how well you approach the improvement. What you also can do is not only segmenting a single phase. Right now we have only said it's background or foreground, but of course in many natural materials we have multiple phases, and this is the first approach towards it. What you in principle have to do, if you just do the thresholding, you have in principle one threshold less than you have classes. So in this case I have 3 classes, and I put the thresholds in here. You see it's nicely separated in the histogram, and that makes it pretty easy to segment these 2 blocks. This one is also separating. In the case when it's so noisy that the histogram are not well separated, then you start, of course, getting misclassifications. And what you typically get is in the class with the lowest values, you mostly only have misclassifications from the neighbor class. Same goes also for the high intensity class, which is also only from the middle class. The middle class, however, gets misclassifications from the 2 other ones. So it's more confusing which ones you have here. So this is only the first approach towards the multi-classification. I will continue next week showing some more examples, what troubles you can get into. An example of multi-class segmentation is this geology clay sample, where we have some X-ray tomography. And we have different classes. We have clay, rock, and air in this sample. Now this one is very dark, but you see some bright spots. Then there is a gray level in the middle and some holes, which is the corresponding to the air voids. Looking at the histogram, it more or less looks like the one I showed before. So we have a central peak, which is the rock. I think. Let's see. I don't remember actually which one is what, but and maybe the rock is the clayest in the middle. Could be actually. And then we have the air voids back on this back end here. And yeah, I was right. Yeah. But what we put thresholds in this image that below 0.3. It's a void. The middle class, the gray mass background is between 0.3 and a half. And you can see it goes pretty wide out in the tail, but still not fully out. And then the rock is beyond 0.5. And if we apply these thresholds, we can see how it turns out. And I would actually say it looks pretty good. There are some, from eyesight, I would say there are some misclassifications, but it's not too bad. The reason why it's relatively good is that the signal-to-noise ratio is pretty good in this image, so there are no misclassifications due to noise. It's more material fluctuations and the choice of where the threshold was set. So I've been talking a lot about just applying a threshold, and the question is how to implement it. And thresholding is one of the easiest operations. In principle, in Python and MATLAB, you just put the threshold, you have the image, greater or less than a threshold. If you want to do multiple thresholds, you can just combine them like this with a ampersand in the middle, and then you get all these classes together. If you want to do it more old style Python, then it gets a bit more complicated line. So it could be that you need it in some cases, but mostly this is the most efficient one. If you would implement a threshold in classic, more traditional programming language like Java, C++, then you have to start writing up a lot of loops where you go through the different coordinate axes, and then, in this case, the position is computed, and then you have to index a big array and setting each individual pixel as a value. With C++, it's essentially the same, no big difference. But in many cases, when you do the implementation, you can reduce the problem to just saying that you have a big chunk of memory and go through all the points and compare them. Then the three loops reduce it to a single one, and it's easier to read. So this is probably what you would do. It's also easy to parallelize. It's in the class of ridiculously parallelizable, so it's just plugging it in. If it makes sense, I am not sure, because it's so fast anyway, but yeah. So what we have from the segmentation is that segmentations are not always so good, and we want to measure how well we perform, and for that we need our ground truth to validate. Either you have data which is already pre-labeled, or you synthesize your own test data to see how well it performs. And if you have multiple phases, you need also to add more thresholds to cope with that. And that leaves us for today from the segmentation part, and instead going to cleaning up, because the segmentation is usually not perfect. And what we need to do is to do some post-processing, and the morphological image processing is kind of a structural filter that looks in the neighborhood and compares if the current pixel should be modified or not. So it's not like in the convolution that you weight each pixel, but it's really just comparing same class or not same class. And well, we can have images like this, and there are a lot of misclassification in those. To clean it up, we need to do something, and that is where we come into the neighborhood operations. And when you want to do the cleaning, you saw also with the convolution that if you have a large neighborhood, it's more computational intense, and it can also cancel relevant features. And on the other hand, if you have a small neighborhood, then it's faster, of course, but you can also have problems of filling large misclassified regions. So you have to balance a little bit on how large neighborhood you're working on. And well, that one we can skip. It's just a general thing about the neighborhood. When you start looking at the neighbors, the first principal ones are the 4 connected neighborhood, which only looks up and down and sideways in the neighborhood. And then we have the 8 connected, which looks actually on all that pixels that surround the current one. Which one you choose depends on what you need to remove and also how gentle you have to be. And we can even have more crazy, creative neighborhoods. We can have disks, so it should be an approximation to a disk. Doesn't really look like one until you go up in the larger sizes. We can have crosses, we can have lines, stars, octagons. All these are predefined in Python in the scikit image package. But in the end, what is practically used is either just a box neighborhood or a disk neighborhood or a sphere if you go up in 3D. All the other ones are a bit more special use cases. And if we go up in 3D, we add a dimension. So now we are not only looking just up, down, sideways, but also in the depth for our neighbors. And of course, we have the 26 connected. Could also look at the 18 connected, which is taking out the corner boxes of this one. So that would be something in between, which is, well, you could claim it's more sphere-like. The basic operations in morphological image processing are erosion and dilation. The erosion removes pixels from the structures you have segmented, and dilation adds pixels. So in principle, you're peeling off a layer with the erosion, and you're coating with the dilation. And what they do is you actually already have these implemented in scikit image. So having this original structure, you see that there are some tiny details. You have holes, you have bridges, and also smaller structures on the sides. If you erode with a 4-connected neighborhood, so this is our structure element, then if you erode it, there is not very much left because you need to fit in the whole structure here. So the only places where you can fill in the full cross are the ones that are kept. Dilation does the opposite. As soon as it feels the contact with the structure, then it adds a pixel. So looking into detail, first the dilation. You can see here that if the cross, if you go to this pixel, the cross has contact with the original structure, then let's make a pixel here. and so on. And that's why it's also growing the whole structure and filling out the holes, and also these gaps between the objects. So you get a very blobby appearance after the dilation. The erosion, as I said before, does the opposite, so it shrinks the structure, and it has to be that you fill in across, then you are allowed to put the pixel in the original image, in the dilated image. And there are only few places in this image that actually result in some structure. So these are the two basic operations, and you can already see that they can be used to remove misclassification, but mostly they remove too much. And that's when we come to using combinations of them instead. So we combine, either we do the opening, we first erode, and then we dilate with the same structure element. Closing is the opposite order, so first you dilate and then you shrink it with the erosion. And if you look at the original, if we do a closing, then essentially the original structure is still there, but the holes and this tunnel here, they have vanished. And they were here, and there was also a hole down here. Maybe I make it a bit smaller, so then you can see it. When you do the opening, all the small structures, they still disappear because there is nothing really to rebuild. And then, well, you get a space invader and a cross out of these two structures. Looking in detail, the first step of the closing is that you do the dilation, so that's the blue pixels here, and then afterwards you erode, and then what is remaining are all these additional green points. So the effect of doing these operations is that you add some pixels on some places, which in principle would also be to some degree misclassifications if you compare them, but it's much better than before. And well, then we have the opening, which gave us from the erosion only these little tiny structures given by the yellow, but from the dilation we grow it out a little bit. Which one you use and depends on what kind of structures you want to target, and sometimes it's even that you do a cascade of opening and closing with different sizes of structure elements. It really depends on what the character is of your segmented image. If you need to do too much opening and closing, then maybe you should go back and redesign your segmentation algorithm. In principle, the erosion and dilation are special cases of the rank filter, which the rank filter is that you sort all the pixels in the neighborhood and then you select one in the order. And the dilation is in principle the local maximum, and the erosion is the local minimum, and in between we have the median value. So that one can also be actually applied to gray level images. So instead of just comparing true or false, you can actually also compute the local max in the neighborhood of the image or of each position. Two more interesting things that we can work with are top hats, and that's a combination of an opening or a closing and the original image. So the white top hat is this original image minus the opening of the image, or we have the black top hat, which is the closing of the image minus the original. And that we can test, again on this cell image where we have this gradient, and that was, as we saw before, pretty annoying because we got smaller items and we even missed some of these cells in this end, and we got two large ones in this end. So let's try with a pretty large top hat on this cell data. And with a white top hat, it looks a bit patchy, a bit strange. If it looks like this in the top hat, it means in principle that you have two small structure elements. And in this example, I used, I think, a radius 15. And that was too small because that structure element can fit between the cells. And then you get biases in the image. So you need to select the structuring element in a way that it always is in contact with one of the relevant objects. The black top hat, on the other hand, manages to actually extract the dots with the cost that it's the intensity is flipped. But that's a quick one to correct for, actually. So what happens if we take the black top hat and compare it to segmenting the original image, is that you saw before that the cells in the original image, they were much smaller up in the left corner than in the lower right corner. And after this correction, they have, visually at least, I didn't do the calculation here, but visually they are about the same in all corners of the image. So this is a way how you can correct for bad background if you couldn't do it with the normalization. And in some cases it's actually not possible. I had one example of a snow profile. So the people in Davos doing avalanche research, they did a profile and made pictures of that. And the pictures got the light that it got, and they couldn't get any flat field image for that experiment. And then they used a top hat for the correction to flatten it, and it worked out pretty well. Problems with segmentation is something called partial volume effect, because images are usually not perfectly sharp. You have some unsharpness along the edges, you have variations in intensities due to material distribution, and so on. And it could be also that the edges are not perfectly filling a pixel, but it's kind of on the edge, and that gives you this partial volume effect. And if you look at a thresholding a structure with different image sizes, here I looked at an image size of 10 pixels, 20, 50, 100, and 1,000 pixels, and you can see that this circle doesn't really look like a circle with 10 pixels. With 20, well, kind of a circle. At 50, it starts looking like a circle. And if you measure the volume fraction for a circle with this small image, you have the volume fraction is 36%, because we lose a lot of pixels or a lot of details of the circle. And it actually goes up all the way to around 44% for this particular circle. And that means you need to have pretty large structures in order to quantify a perfect shape, if you want to have the perfect shape. Sometimes it's sufficient to have these small thingies, but then you have to know also that it doesn't describe the shape very well. And the same goes for spheres. If we have a small sphere, here I did an analysis where I took the discrete sphere, so I thresholded a sphere in the image, and then I computed the analytical from the geometry definition of a sphere volume, And I tried that for very many radiuses, and you can see that in the beginning, the error in volume is pretty great, pretty large here, beyond 20% error. And then when you come to about radius of 10, then you're down to 1% error in the volume compared to the analytical volume. And you have to go pretty far out to come to a small error of this sphere volume. So this is something to also be aware of when you start saying, okay, counting voxels, that gives me a volume. It's not fully true. And if you want to do it really correctly, you should do some kind of analysis where you quantify how big is your error in this. Rescaling is another problem. It's not uncommon that you have a large image and you say, oof, that's too big, I downscale it. And then we see in principle the same effect as we saw before, that downscaling a 1000 pixel image gives you this volume of 44% that we had before, but downscaling it to different levels here gives you more and more errors. And you can even see that the downscaling, this is difficult to see in this light, but the downscaling even gives you some grayscale corners, so it's not even a black and white anymore. And these are the profiles. They don't show these effects here because I hit it too well. But you see that there is kind of a more and more tilted edge along these edges. Another thing that happens when you do the downsample is that you get these interpolation edges, which are a different color. And if you have the high resolution image and say you want to downsize it to pixels with these, according to this grid pattern that I have introduced, you can see that this one is no problem. But if you come to the edge, then it's really the question how to handle it. Do you want to do a strict threshold on this downsampled edge, or you want to do, say, a percentage of the intensity from that edge? And if you would do the downsampling, you see here that the edge gets a bit smooth. So this one, for example, doesn't have much contribution, so it's pretty dark. This one has much more contribution, so it's brighter. Then if you would apply the threshold on this edge, you see that instead of having a smooth line, you get this boxy pattern when you segment it. That's also an effect that you need to be aware of when you apply downsampling on images. Ooh, that was big. So today, in the second part, we looked at, well, actually the whole day, actually. We looked at the image formation process, how images are formed, also how we can use the histogram for finding a basic threshold. The evaluation of the performance is something you should always build into your workflow, making sure that it actually does what you want, and see if you need to improve somewhere, what kind of improvement you can do. You can apply filters to make the histogram easier to handle. In some cases it helps, some cases it doesn't help. And if you got your misclassifications, the morphological image processing can actually help you to clean out some of the misclassified pixels, but here it's important also to know that you in some case you distort actually the edges, and that could be a nice exercise actually to check what is the ROC curve if you apply these opening and closing operations on your segmentation. And when you do the segmentation, you also have to be aware that you have these partial volume effects that you don't actually perfectly hit the edges, and if you have small items, the real structure is not always so well represented as you would like it to be, and that can give you also errors in measurements later. Yeah, and that was in principle all for that. And next week I'm going to look into how you can automate the whole segmentation process. Right now we have just taken some value, looks good, go ahead. Next week we're going to look into algorithms that actually find the threshold for you based on statistical methods, and then you hopefully get more robust with the segmentation task. So, thank you for today.